Okay, so in our last video, then we talked about how our principal energy levels inside of the electron cloud are kind of like probability distribution maps. We kind of see like this general area where we're likely to find electrons and areas where we are not likely to find electrons. So when we take a look at this, we've also seen a couple other important things. We can either know position or velocity when it comes to an electron. And the more certain we are of one, the more uncertain we become of the other. And this also means that position and energy of an electron are in the same boat. I can know the position or the energy, and the relationship here is the fact that our kinetic energy is equal to 1/2 times the mass times the square of the velocity. So because of these connections, we'll see that these pieces are kind of interchangeable with each other. So in this case, we can either give the energy or its location, but we can't do both. So what we can do is we can give a probability of finding a location and approximate energies for what that is. So in this case, when we talk about an electron's position, we're going to find that the resulting function is something called an orbital. And this orbital is the probability of finding an electron in a particular spot. And in this case, since it's a probability, we can actually graph this out to see what the probability density looks like. So in this case, the connection between these two is written by something called Schrodinger's equation. So when we take a look at this, we'll see that there's two pieces that have to do with this. So in this case, we have the wave function. And in this case, the wave function describes the wave-like nature of the electron. When we take a look at our this h hat here, this is actually called the Hamiltonian Operator. And this just means it's a given set of mathematical operations that you can do in the same order on the wave function. And what you get out is this thing called an eigenvalue, or in this case, you can kind of think about it like the energy of an electron. And this is one of the most famous equations that's out there. It's called Schrodinger's equation. And there are some really, really complex functions here that we're not going to get into because we don't have differential equations or linear algebra as a prerequisite for this course. However, there is an important piece here. When we take a look at how this is solved, we end up with a different series of eigenvalues that come out, and this leads to the square of our wave function becoming a probability density or a probability density graph. And the resulting shapes of these graphs then lead us to these different solutions of our orbitals and what our orbital shapes look like. So in this case, to describe the orbital shapes, we use something called quantum numbers. And these quantum numbers describe electrons in certain orbital shapes. And so there are a few that we look at. The first one is the quantum number n. And in this case, this is the principal quantum number. And what this does is this describes the energy level. So in this case, if I were to take a look at the Bohr model of the atom, you can think about it like the principal quantum number is which ring the electron is in, or which orbital the electron's in around the atom. From there are a couple other quantum numbers that are set up. There's the quantum number L, which in this case is the angular momentum quantum number. You may also hear this called the Azimuthal quantum number, depending on which text you're reading. And there's one more. There's one more called the M sub L, which is the magnetic quantum number. And so when you go to plug some of these specific pieces in, we'll see that we can take a little bit of a different look at some of our principal quantum number information. And in fact, when we take a look at these principal quantum numbers, we'll see that this n equals 1, n equals 2, n equals 3, you can actually determine the energy of the orbital that it's in. So what you can do is you can realize that the energy of any given principal quantum number, or the energy of any given principal energy level, is equal to negative 2.18 times 10 to the negative 18 joules times 1 over n squared, where n is the energy level number. And so all you'll need to do is plug this in. Now there's an important thing here that you'll notice. In this case, it's a negative energy. And this is because of the negative, that means energy is released because the electron becomes closer to the nucleus. And in this case, it has to give off energy because of the attractions that help to stabilize it. So when we take a look then at our next set of quantum numbers, we're going to see that there are kind of a different piece. So when we take a look at this angular momentum quantum number, this will determine the overall shape of the graph that we see. Because it turns out within each energy level, there's another level of organization. And so when I take a look at my azimuthal quantum number, or the value of L, we can kind of come up with a letter designation, and we're going to go over each letter here in just a minute. I can have L be 0, 1, 2, or 3. If it's a 0, I designate it as an S for a spherical orbital, P for a single node, D, and then F. And so each of these shapes, or each of these values, has their own shape. And lastly, our M sub L quantum number, my magnetic quantum number, tells me the orientation of this orbital, helps me determine what axes we're looking at to make this work. And there are a couple important things to keep in mind for quantum numbers to be valid. In order for a quantum number to be valid, we have to see that L is any value between 0 and n minus 1. Where n is that principal energy level. So in this case, if I see that n equals 2, if I'm in the second energy level, then L has to equal either 0 or 1, n minus 1 being the maximum value. The other thing is that m sub L has to be an integer between plus L and minus L. So that means if L equals 1, then m sub L has to be one of -1, 0, or 1. So what do we do with all this? Like, they've come up with these quantum number designations, but what this allows us to do then is kind of create a secondary, more in-depth organized electron system within our energy levels. So what I'm going to do is I'm going to draw a larger picture here. So I have my energy levels over here, n equals 1, n equals 2, and n equals 3. What we're going to do is we're going to take a look at the different quantum numbers we can see within each level. So in this case, if n equals 1, L has to be equal to 0. And so what this means is I only have one orbital called a 1s orbital where I can have electrons. Since L equals 0, that means that the m sub L of this orbital has to equal 0 as well. When we take a look at the second energy level, though, I'll see that I can have my L equal 0 or my L can equal 1. So what this means is that my value of m sub L can only be 0, so I can only have one type of orbital in the s orientation. Whereas over here, I can see that my m sub L can be equal to -1, 0, or 1. And as a result, I'll see that there are 3 different types of orbitals in something called the 2p orbital. And this would be the 2s orbital. And when I go up to the n equals 3, we can see my L can be equal to 0, L can be equal to 1, L can be equal to 2. If my L equals 0, there's only one satisfiable value of m sub L, and that would be the 3s orbital. I can have m sub L equal to -1, equal to 0, or equal to 1, and I can see that there's a set of 3p orbitals. And then lastly, I can see I have 5 different values where my m sub L values can be -2, -1, 0, 1, or 2. If this is the case, we see that we're in the L equals 2. We call these the 3d orbitals to set these up. So when we take a look at this, there's kind of a few important rules that we have to follow. When we take a look at our principal quantum numbers, we'll see that the total number of orbitals in any energy level is equal to n squared. So for example, in the first energy level, I only have one possible orbital because 1 squared is 1. In the second energy level, I have a total of 1, 2, 3, 4 orbitals, which is equal to 2 squared. In the n equals 3, I have a total of 9, which is equal to 3 squared. So you'll notice that kind of as we go up, everything works out pretty well. There's going to be one final quantum number that we can look at for this, and this helps to distinguish one electron from another. And this kind of goes to the final quantum number called the spin quantum number. And this has to do with the direction the electron is traveling. And in this case, you can see that your m sub s, your spin and quantum number, is equal to plus or minus 1/2. If your value is equal to 1/2, your electron moves up. If you're minus 1/2, your electron moves down. And we'll talk a little bit more about this in our next unit. But one thing that I want to do then is kind of use this model and all of these orbital shapes to show then how our we can use this quantum model to then explain spectroscopy. When we take a look at an electron that's jumping between energy levels, we kind of learn that our principal energy levels get a little bit closer as we move up. So in this case, this will be my level, and I'll say my lowest is n equals 1, n equals 2, 3, 4, 5, 6. Okay, so there's our different energy levels that we have. We remember that when we take a look at how big the energy jump, what happens here, I should say, is my electron that's starting here ends up absorbing energy, and it promotes or it excites to a higher energy level than it was before. And so then what ends up happening is we'll see that there's going to be some kind of relaxation once that energy source is removed, and that energy source of that jump of relaxation determines the color of emission. And there are all kinds of orbitals all the way across the board for each different atom. So when we take a look at this, we'll see that things like n equals 5 down to 1, 4 to 1, 3 to 1, anything back down to the n equals 1 energy level is an ultraviolet transition. Anything down to 2 is visible. And anything where it drops down, any relaxation to 3 is going to be infrared or IR. So let's do a quick example here. Let's take a look at a hydrogen atom, or an electron in a hydrogen atom. Relaxes from n equals 3 to n equals 2. Let's determine the color of light that's emitted. Or in this case, the color or the wavelength of light emitted. So in order to do this, I'm going to have to remember a couple important things here. That we can determine the energy level, or we can determine the energy of any orbital. So in this case, the change in energy is going to be directly proportional to hc over lambda. So what I have to do is I have to figure out the energy first by looking at the energy of n equals 2, and I take away the energy of n equals 3. So I use that equation that we had from last time, 2.18 times 10 to the negative 18th joules over 1 over 2 squared. And then that's E of n equals 2. And then I can find out the energy of n equals 3 by doing the same thing. So when I plug this in, then I can kind of rearrange this and say that delta E is going to be equal to negative 2.18 times 10 to the negative 18th joules over 1 over 2 squared minus 1 over 3 squared. And when I plug this value in, I see that my delta E value ends up being negative 3.03 times 10 to the negative 19th joules. So now what I'll do is I can plug this in to my earlier equation. And I know that negative 3.03 times 10 to the negative 19th joules equals hc over lambda, so 6.626 times 10 to the negative 34th joule seconds times the speed of light. And I divide that by lambda, which is what I'm solving for. So after doing a little bit of algebra and rearranging, I end up with this expression. I have 3.00 times 10 to the 8th meters per second, and I have negative 3. I have 3.03 times 10 to the negative 19th joules. And again, this means energy is released. Sorry about that. A little side note. So my joules cancel, my seconds cancel, and my units are going to leave me with meters. All my wavelengths have to be in positive setups because remember, the change in energy of the atom is equal to the negative energy of the photon. And that's kind of what we're plugging in here. So that's why that negative becomes a positive. So lastly then, I see that my lambda value comes out to be 656 nanometers. And this is a red color that we observe in the emission spectrum of hydrogen. So with that, you can then take the same idea and apply that to any energy level in hydrogen that you're looking for. So lastly, the thing that I want to talk about is what these shapes look like. So when we take a look at each of these, we said that there's like this secondary organization system, and we're going to need the shapes of each orbital to make this work. So in this case, anytime I have like an s orbital, it is a sphere. When I have a p orbital, it's kind of like an infinity symbol. A d orbital generally looks something like that. And an f orbital has 3 lobes, and that's going to look a little differently. We'll see that there's a whole bunch of different f orbitals that work out. But in this case, you can kind of see like we have an x, y, z plane. I have some coming off in the back and some that are in the front. And I see that's the case for every setup that we have. And again, it's kind of like a d orbital, only in 2 sets of d orbitals, only in 3 dimensions. And there are all kinds of different shapes that you can observe for your energy levels. But be aware that my 1s orbital is kind of a sphere in the principal energy level. And when I take a look at the second one, I'll see that it's the same idea. I kind of have the spherical shell shape around the 3s. And that's kind of where we get the idea, or the rough approximation, that we kind of have like these individual energy rings. And what you'll notice is that there's kind of a region where there's no electron density. And you'll see that this applies for every single set of orbitals. So when we take a look at the probability density, or the square of the wave function, as we take a look at the radius of the atom, and we're going to do this on scales of about 100 picometers, we're going to see that we end up with some interesting shapes. And we're only going to take a look at what the first 3 looks like, but this comes down. Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 11, 12. 12, That means this is 6. Okay. So when this comes down, we see that there's a node right at about 150 picometers. And then we'll see that electron probability gets pretty high as we go up. And then it comes down again and hits another 0 right around 400 picometers. And then we'll see that my peak gets a little smoother as it comes out, and I start to see that my 0 approaches right around 10 or 11. So what this says is that every time it hits 0, this is a node. And you'll notice that as we get farther away, the nodes are at a larger distance as we go out. And we'll see that this is going to be there for every orbital. So in this case, when we take a look at the shapes of an atom, we say they're roughly spherical because it's got all of these shapes. I've got p orbitals in the x and y directions and the z directions. And each of these has their own plus and minus phase associated. Plus and minus meaning that this is the origin right in the middle of the node, and we have either a positive value or a negative value for the electron spin. And this plus and minus is going to be pretty important when we start talking next unit about how each of these line up. But when you combine all these atomic shapes into one, you end up with a roughly spherical idea of an atom. So thanks for tuning in. This wraps up our discussion on Chapter 2, and we will take a little bit more about how the quantum mechanical model of the atom impacts chemical reactivity when we start Chapter 3.